Okay. So when we're looking at this, what we're going to do now is, because these rate laws can only be determined experimentally, we're going to look at writing rate laws from experimental data. So if we look at sharing my screen here. We are going to look at this set of information. So we have a reaction that 2A plus 2B plus C gives us 3G and 4F, right? And we ran a series of experiments where we changed the concentrations initially of A, B, and C, and we recorded or observed the rate that that reaction was occurring. Right? So from this information, the balanced reaction and the experimental data, we are going to determine the rate law for the reaction, determine the rate constant, give the overall order. Right? So again, like we said last time, we can talk about the rates in terms of each individual reactant. We're going to have something that relates each individual reactant. That's called the order. The sum of them is going to be the overall order. And then we're going to use that information to predict this rate of experiment 5. Okay. So in general, regardless of the, well, not regardless, but if we look at this chemical reaction, we are going to focus for the rate law on the reactants, right? We're only concerned with the reactants because the products just happen, right? We're interested in how fast those reactants change, right? And in general, that we can say that the rate of this equation, or this reaction is occurring, is equal to some rate constant lowercase k times the concentration of each one of those reactants, right? And each one of those reactants is going to be raised to some exponent, and they could be the same or they could be different. So I'm going to call them X, Y, and Z. All right. So that's the general form of the rate constant, or rate law, excuse me. Right? Rate is equal to lowercase k, the rate constant, times the concentration of each reactant raised to some coefficient. Right? And it's important to note, let's change this back to red, that X, Y, or Z are not related to the coefficients. I'm just going to abbreviate it there because I can't spell coefficients today. Right? These numbers up here. Right? It may work out that they are the same, but they are in no way related. The only way we can determine these values is by using this experimental information. Okay. So the way we're going to do that is we're going to look at good experimental science where we change only one variable and see the result of that variable. So we're going to look for two reactions where the concentration of two of those reactants, or two experiments, excuse me, where two of the reactants are not changing. Right? So for example, we can look at experiment 1 and experiment 4, right? In experiments 1 and 4, A and B are staying the same, C is changing, right? So any change in the rate is going to be a function of only C. And when we do that, we are going to essentially set up to a ratio, right? That the rate, I'm going to look at these, since this is the larger number, I'm going to put that one on top. So rate of experiment 1 is equal to the rate constant of that experiment times the concentration of A in experiment 1 times the concentration of B in experiment 1 times the concentration of C in experiment 1. And we're going to divide this by the rate of experiment 4, the rate constant, and the concentration of A in experiment 4, concentration of B in experiment 4, and the concentration of C in experiment 4. So if we put those numbers then in, we're going to see that the rate in the first one, which is 2, divided by the rate in 4, which is 2, is going to be equal to this rate constant, lowercase k, divided by the rate constant, lowercase k, times the concentration in 1 divided by the concentration in 4 times the concentration of C in the 2 experiments. Everybody follow? All right. If we examine this now, these two, the K's are the same, so they're going to cancel out, right? We have 10 to the X and 10 to the X, so those are going to cancel out. They're going to go to 1, essentially. The 100 to the Y and 100 to the Y are going to cancel out. We're going to have that go to 1. So this is going to be equal to 2.0 over 2.0, which is 1, is equal to 700 divided by 400. Since they're both have the same exponent, we are going to combine those and put the exponent on top because of math, right? And when we do that, we end up with 700 divided by 400, which is 1.75. Let's actually do that math. I'm not trusting myself. So this is equal to 1.75 to the Z, right? So what do we have to raise 1.75 to get 1? Because these two are equal, right? And in fact, if we want 1 from any number, then to get that, we say that it has to be 0. So Z is equal to 0, because raising any number to 0 will give you 1. Okay. Questions on that, right? So now we can replace this Z with 1. Right? And we're going to repeat that process for the other two values. So we need to find 2 places where A is the same and B changes, right? We can no longer, because the exponent for C is 0, this is not going to have any effect on our rate, so we can sort of ignore it, right? Because whatever value that is going to become 1 because we're raising it to a 0. Right? So now we want to find a place where A changes and B stays the same. So we're going to look at experiments 1 and experiment 2, right? A is changing, B is staying the same. And we're going to do something similar, right? We want the number that's larger on top because we like to work with whole numbers and not fractions. So we're going to put experiment 2 on top of experiment 1. So rate of experiment 2 divided by the rate of experiment 1 is equal to the rate constant times the concentration of A raised to the X for 2 divided by A raised to the X for 1, B raised to the Y for 2 over B raised to the Y for 1, times c to the 0, because we already know what that is. Right? So then, help if I could remember numbers. So the rate of 2 is 4, the rate of 1 is, so we're going to get 4.0 divided by 2.0 is equal to, now just like before, this cancels and that's going to cancel. So we're going to be left with the concentration of A on this one, because it was constant, is going to cancel. So we're going to just get the concentration of A in experiment 2 divided by A in experiment 1, which was 20 divided by 10, all raised to the x. So now we have 2 is equal to 2 raised to the x. So what do we have to raise 2 to get 2? The answer is 1. And we are going to repeat that same process with for B. Now we want A to stay the same and B to change. So we are going to use experiments 2 and 3. Right. And we can set it up, but I'm going to take the shortcut. So we're going to take 16 divided by 4 is equal to 200 divided by 1. 16.0 divided by 4. Is that what I said? Can't remember. Yep. Is equal to B 200 divided by 100 raised to the y. All right. So we get 4 is equal to 2 raised to the y. What do we have to get raised 2 to get 4? The answer is 2. Right. So now we can rewrite the rate law as rate is equal to rate constant lowercase k times a to the first power times b to the second power times c to the 0. Right? Or we can just write it as rate is equal to lowercase k, a to the first, b to the second, right? Ignoring c. I will always include it this way because I want to make sure that it's still there, right? That I take into account and know that it's 0 and just that I didn't forget it. So you will always see me do this. But I will accept the other one. Okay, so that's the first part. The second part, we have to determine the rate constant. Right, so we can pick any of these experiments. Right, now we know the rate, we know the concentration, and we know the orders. So the only unknown in this now is this rate constant K. So let's pick experiment 3, right? Just because it's Thursday. So we are going to say that in experiment 3, right, the rate is equal to rate constant over a to the first, b squared, c to the 0. So in experiment 3, that is, so our rate constant K is equal to rate divided by the concentration of A to the first, B to the second, C to the 0. So this is going to be 16 divided by, would help if I could remember numbers. I keep saying that. 20, 200, 200. And we do that math, we end up with a number. So do that math, and what number do we get? End up with 2.0 times 10 to the minus 5, right? If we look at the units here, this is molar per second. This is going to be molar, molar, molar. So our units here are going to be, oh, sorry, that's millimolar. Millimolar to the -2 seconds to the -1. Because we have 3 millimolars on the bottom, 1 on the top. So 3 minus 1 is, or 1 minus 3 is -2. So that's going to be our rate constant. If we look at the overall order, in this case is going to be x plus y plus z, which is equal to 1 plus 2 plus 0, or 3. And we can also, these two should be related. When we talk about the units for our rate constant, lowercase k, it's going to end up being some unit of molarity to the 1 minus overall order. Actually write that so you can read it. 1 minus the overall order, and seconds to the -1. Right? Okay. Questions on that? Okay. So now we have the rate law, the rate constant, and the overall order, and we can actually substitute all those numbers in here. So we get rate is equal to 2.0 times 10 to the -5, molar to the minus, or millimolar to the -2, seconds to the -1, A to the 1, B to the 2, C to the 0 if we want. And the last thing we're asked to do is calculate the initial rate in experiment 5. So in this, we have the rate is equal to K, oh, sorry. (2.0 times 10 to the -5 millimolar to the -2 seconds to the -1 times A to the 1, B to the 2, C to the 0. So if we look at that, our rate is going to be equal to 2.0 times 10 to the -5 millimolar to the -2 seconds to the -1 times 4.62 millimolar to the 1, 0.177 millimolar to the 2 times 12.4 to the 0. Is that right? So when we do all of that math, our rate is going to equal 2.89 times 10 to the -6 millimolar seconds to the -1. Okay. Questions on any of that? So the last thing that I want to talk about is if we come up here, right, when we were doing these comparisons to calculate the rates, right, we can easily estimate what these are, right? You know what you have to raise 2 to get 2, or 2 to get 4, right? We can do that math in our head, right? Because of the wonderful things we learned back in elementary school, right? Our multiplication tables. If we don't know how to do that, we can solve this problem, right? To solve using math, what we're going to do is we have to get rid of the exponent, right? In order to get rid of the exponent, we need to take the log. So in this case, we are going to take the log of both sides. So we're going to take the log of 4 is equal to, now when we take the log of this, that y comes in front, right? So the log of 2 to the y is the same as y times the log of 2. Right? So then we're going to get the log of 4 is equal to y log of 2. So y then becomes the log of 4 divided by the log of 2. Right? So that's if we have a number that we can't do in our head, or if we want to just be lazy, if you will, right? Not looking at doing estimations in our head, we can always use the logs to solve that. And the last thing that I want to mention is that we typically refer to these orders as whole numbers because it makes sense, right? If we go back to this reaction, if we talk about atoms, we have to have some whole number, right? And this rate law is really telling us, gives us a sense of how this molecule is reacting as it goes from reactants to products and how many molecules are involved, right? If we think of it then on a molecular level, these orders should be whole numbers. But because all of these reactions don't necessarily occur in one step, right? A, B, and C do not all combine in order to get products in one step. We actually can find that experimentally, these orders can be non-whole numbers, right? If they're close to a number, if we calculated it was like 1.9, we could round that to 2. But if we could also calculate it where it's like a 1.5, and that would be fine. Right? So if it's close to a whole number, feel free to round. If it's not, just leave it alone. Okay. Questions on that? Any questions before we